Welcome back everyone to a session on Unix programming. In the previous lecture video, we have seen an IPC mechanism called message queues, right? We saw the various functions associated with message queues and its working. In today's session, we will look into another IPC mechanism called as semaphore. Okay, and you might have already seen semaphores in process synchronization, in a concept of process synchronization when you have studied operating system, and the same concept is used here. So using the semaphore, we can restrict multiple processes accessing the shared resource, right? So let us see how exactly semaphore works. Semaphore is a counter used to provide access to the shared data object for multiple processes. Okay, so the name might be very complex, but it is actually a simple counter, and it is used to restrict access to some shared resource. So let me write this as one resource R, and each resource will be having its associated semaphore. Okay, it's a counter value, and it will be having some positive value. So this is the semaphore associated with the resource R, and let me take the value as 2. Of course, there is something called as binary semaphore that has only 2 possible values, 0 and 1. Here we don't have a, here I have not represented a semaphore as binary, but I have mentioned some positive value, and I took the example as 2. Okay, so let us see what happens, or how the process will be able to access this resource based on the semaphore value associated with this particular resource. Okay, so to obtain the shared resource, the process needs to do the following. One is test the semaphore that controls the resource. Yeah, we are talking about this particular semaphore that actually controls the access to this particular resource R. Okay, yeah. If the value of the semaphore is positive, then the process can use the resource. In this case, the process decrements the semaphore value by 1, indicating that it has used 1 unit of the resource. Okay, so this point is very simple. See, suppose there is one process. Let me name it as P1. Okay, so this process want to access this resource R. So if it want to access the resource R, first it will test the semaphore value. So if semaphore value, if it is positive, which is true in this case, right? So if the value is positive, then the process can use the resource. So since S is equal to 2, in this case S is equal to 2, right? So the process P1 will be able to access the resource. Okay, but when it access the resource, what it does is it decrements the value of the semaphore by the value 1. Okay, so it decrements the value of semaphore by 1. So the current value of semaphore will now be, after P1 accesses, will be, yeah, let me write the updated value. S is equal to 1. So this will be the new semaphore value associated with R. Okay. Yeah, if it is not positive, in case if the semaphore value is 0, so let me consider an example. Now there is another process P2, even it want to access the resource R. So what it will do, it will check for the semaphore value associated with the resource. Since the semaphore value is 1, what it can do, even it can access the resource, but as soon as it accesses the resource, what it does, it changes the S value to, by decrementing one value. So the S value will be, now the latest updated value of the semaphore is 0. Okay, now the two processes are currently accessing the resource. Okay, now let me consider this scenario, third point. Okay, P3, now comes P3. P3 is now again want to access the resource R. So what it will do, it will check the semaphore value. Okay, now the semaphore value is not positive, it is equal to 0. So if it is equal to 0, the process goes to sleep. So this P3 will go to sleep. So because it cannot access the resource, since it is already occupied by 2 other resources, that is the maximum accessibility with respect to this resource. At a time, only 2 processes can access it. So that is done by P1 and P2. So P3 has to sleep now, and that is indicated by the value of semaphore S is equal to 0. Yeah, and when the process it sleeps until the value of the semaphore is greater than or equal to 0, and when this happens, the process wakes up, it returns to step 1. So it again tests the semaphore. If the value is greater, then it will be able to access. But now the question is, when the value becomes greater than 0, let us see when the process that is done with the shared resource that it controls, that is controlled by the semaphore, the value of the semaphore is incremented by 1. Okay, so P1, assume that P1, which was currently accessing the resource R, is done with accessing. It has done all the work with respect to this resource. Now it doesn't need this resource anymore. So what it will do, it will come out of, or it will release the resource R, what it was accessing, and while releasing the resource, it will increment the semaphore value associated with this resource by 1 value. So what will be the current value of semaphore is 0. Now when P1 releases the resource R, it increments the S value. So now S value becomes 1. Okay. When the S value becomes 1, P3, which was sleeping, it was waiting for the semaphore value to become positive. It now checks, and it comes to know that semaphore value is now 1. So what it will do, it will be able to access the resource, but while accessing the resource, it makes sure that the semaphore value is again decremented by 1 value. So the S value becomes 0. So this is how the semaphore works. So it is simply a counter that is associated with the resource, and each time when a process wants to access a resource, it decrements the semaphore value by 1. Okay, and if the value of the semaphore, if it reaches 0, then the further process cannot access that particular resource. And when if a process wants to access a resource, and if it finds the value of the semaphore to be 0, then it goes to sleep. And the process which are currently accessing the resource, when it wants to release the resource, it releases the resource by incrementing the semaphore value, and the process which wanted to access the resource, which was currently sleeping, checks the semaphore value, and it can access the resource again by decrementing the semaphore value. So this is how I can have a controlled access to the resource based on the semaphore value. The implementation of semaphore with respect to system 5 IPC mechanism is much more complex than what we know about semaphore, what I said about semaphore in the previous slide, right? So there are 3 features that contribute to this unnecessary complications. The first one is semaphore, as we know, it is supposed to be a single non-negative value, right? But it is not the case. Instead, we have to define a semaphore as a set of one or more semaphore values. So this is one of the flaws, one of the complications in terms of implementation of semaphore. Second one is the creation of semaphore, which is done by using semget function, is independent of its initialization, which is done using semctl function. And this is a fatal flaw, since we cannot atomically create a new semaphore and initialize the values of this semaphore set. It is not possible, because we make use of 2 different functions for the creation as well as for the initialization, right? And the last one, the system 5 implementation, all the IPC structure will remain in existence even when no process is using them, right? So we have to worry about a program that terminates without releasing the semaphore to which it has been allotted to. So again, some other additional features is required to overcome this problem, right? There is a possibility that program may terminate without releasing the semaphore. So if that is the case, the other programs or other processes may not be able to access the resource associated with the semaphore. The kernel maintains a semid data structure for each semaphore set. Okay, so this is maintained by the kernel, and it looks something like this. Semid data structure, sem stands for semaphore ID data structure, and these are the various members. Of course there are many more, but these are some of the prominent members. So this sem permission, obviously it stands for, this is the concept what we have come across when I explained about the general features of system 5 IPC structure, and it is also present in shared memory as well as in message queue, right? The first one, this one, IPC permission. This is with respect to the permission and accessibility to the various processes. Okay. Second one is sem underscore n sems. So this is nothing but the number of semaphores in a set. As I said, the semaphore is not a single counter, but rather it is a set. So this is nothing but the number of semaphores in a set, and this represents the last sem operation time, and the last one, C time, represents the last change time. Okay, so these are the prominent members of the structure sem id underscore ds. Okay, and each of the semaphore is represented. So this is for the semaphore set, right? So each of this semaphore is present in the set is represented by an anonymous structure containing at least the following members. Okay, so this is the structure for the semaphore set, and for each of the semaphore present in the set, I have this this particular structure, anonymous structure. Okay, so we don't have a name for it. It is said that it is anonymous. Okay, sem value. So semaphore value, which is always greater than or equal to 0. Then PID, sem PID, PID for the last operation, the process ID. Then sem count. This is the number of processes awaiting when the sem value is greater than or equal to the or greater than current value, and sem z count. This is nothing but the number of processes awaiting when the sem value is equal to 0. Okay, so this is about the structure of semaphore. This is the structure for semaphore set, and this is a anonymous structure for each and every semaphore present in the set. The first function what we will be using is semget function, which is used to obtain the semaphore ID for the further functions, right, for the processes to access the semaphore. So this is the process of creating a semaphore or opening an existing already created semaphore, and the function is this semget, and these are the parameters that are passed, and it will return a semaphore ID if okay, or if the function is successful, and -1 on error. Okay, and as you all know, key is nothing but the generation of the key we have seen in our previous video when I explained about system 5 IPC mechanisms. So this is a general way of creating a key for all the 3 IPC mechanism: message queue, shared memory, as well as for the semaphores. Okay, so the key is passed as an argument to semget function, and these are the when a new set is created, the following members of the sem id data structure are initialized. So what are those? The permission structure is initialized, and the mode member of the permission of this structure, of this permission structure, is set to the corresponding permission bits of the flag that is specified here. Okay, so the permission, if I want to set the initialize the value of the permission associated with this semaphore, then I have to set the mode value, and the mode value is specified through the flag values what is passed into the semget function. Okay, correspond, yeah, so that is the that's what it means in this particular point. Then semaphore O time is set to 0, semaphore C time is set to the current time, and sem n sems is set to n sems. So this is nothing but the number of semaphores that is required in the semaphore set which I am going to create, isn't it? So if I pass the value as 5, then 5 semaphores in a semaphore set will be created. Now if I So this need to be specified when I am creating a semaphore. If I am already if I am opening an already existing semaphore, then I have to specify the n sems value as 0. Okay, and this O time represent, what does this represent? This represent the last semop operation time, okay, which we will be looking. Semop is the function which we will be seeing in the future, in the next in the upcoming slides, and semc time is nothing but the last change time in the semaphore value. Okay, so this is about semget function, which is used to get the, or which is used to create a new semaphore or open an already existing semaphore. The next important function is semctl function, with which I will be able to perform various semaphore related operations, and its syntax looks like this: semctl. And these are the various parameters that are passed to this semctl function. The first being semid. So I want to specify on what semaphore set I have to perform the operations. So that is specified by using the semaphore ID. So this is an ID to the set of semaphore. And second argument is sem number. Sem number is nothing but a individual semaphore present within the set. Okay, a set contains multiple semaphore, and if I want to perform operations on one of the semaphore belonging to the set, then that is mentioned by using the second argument, which is nothing but the sem number. And third argument is nothing but some of the predetermined operations what I want to perform in terms of a command. Okay, so there are 10 commands that I can perform on the semaphore, which we will be looking very soon. And the fourth argument is optional. That depends on the command that is requested, and if it is present, it is of the type union. Okay, it is of the type union. We name the union as semaphore union, sem un. Okay, and it is a union of various command specific arguments. So this is the union. Okay, it has these values, and this will be used along with the command. We will be looking into that very soon. Okay, interval, where it is used. It is used when the command is setval function, and the buffer is used when I make use of IPC stat and IPC set, and an array is used when I make use of getAll and setAll command. Okay, so this is the command what I was talking about. This is the third argument, right? So third argument is command, and these are the predefined commands. Okay, so with getAll, I should be able to return the values of the semaphore set in the arg.array, which is mentioned in the union, right? Which is mentioned in the union. As specified, getAll and setAll function makes use of this. Then getVal, it returns the value of a specific semaphore element. Okay, I'm not talking about entire semaphore set, but within a semaphore we have semaphore set, we have multiple semaphores, right? So I should be able to return the value of a specific semaphore element using getVal function. GetPID returns the process ID of the last process to manipulate an element. Then getNCount returns the number of process waiting for an element to increment, and get zCount is it will return the number of process waiting for an element to become 0. Then IPC RMID, very similar to the IPC RMID what we use for message queue. It is used to remove the semaphore set identified by semid. So it will be, the entire semaphore set will be removed. IPC set sets the permission of the semaphore set from the argument buffer, which is specified in this union argument buffer, right? Okay, the second this one, IPC stat, it copies the members of the semid data structure of the semaphore set into the argument buffer, and setAll function, it sets the values of the semaphore set from the argument array, again from this is present in the union, and setVal function set the value of a specific semaphore element to the argument dot val. Okay, that is here, argument dot val. Okay. Yeah, so we should know the difference between the two. setAll, it sets the value for all the semaphore belonging to the set, and set val sets the value of a specific semaphore element present in the set. Okay, so these are the various operations what I can perform on the semaphores by using sem control function. The last operation what we are going to perform on semaphore is by using the function semop function, and this semop function atomically performs an array of operations on semaphore set, and this is the syntax. So this the first argument that is passed is semid, which identifies a semaphore set on which the operation need to be performed, right? So we have to pass it to the semop function. This is the first argument. The second argument, as you can see, the sem operation array is a pointer to an array of semaphore operations, and it is represented by sembuff structure, which is written here. Okay, so this is a pointer to an array of semaphore operations, and it is represented by this structure sembuff. As you can see, these are the various members of the structure. The first one is sem number, with which I should be able to identify the member in the set, right? So when I talk about the member in a semaphore set, I am talking about the individual semaphore present in the set, and this values, the value of semnum ranges from 0 to n sem minus 1. So if the semaphore set contains n sem value as 10, it contains 10 members, right? And the initial semaphore value, individual semaphore value, starts from 0 to 9. So with which I will be able to identify a particular semaphore belonging to the set or present in the set. Second one is sem operation. So this is nothing but the operation that I want to perform. Okay, so its value can be 0 or positive. So we will be looking about this in detail very soon. And the last one is a semaphore flag with respect to IPC no wait and sem undo. So these are the two flags which will be set or not set as per the requirement of the operation. And the last one, no number of operations. So this argument specifies the number of operations in an array, in this array. Okay, so total number of operations what we are going to perform on the semaphore is present here. So if I have the value as 5, then 5 operations we are going to perform on the semaphore, which is present in the semop array. Okay, yes. Now let us see the various possible value of semop and its equivalent meaning. Okay, so if the semop element operations are the values specifying the amount by which the semaphore value is changed. Okay, so this element operations are it specifies the amount by which the semaphore value has to be changed. So if the semop value is an integer that is greater than 0, then the semop function, it adds the value to the corresponding semaphore element value and awakens all the processes that are waiting for the element to increase. So this is what happens if the semop value is an integer that is greater than 0. So what happens if it is equal to 0? If the semop is equal to 0 and the semaphore element is not 0, okay, semaphore element in the sense the individual semaphore, if its value is not 0, then semop function, it blocks the calling process which are waiting for 0 and increments the count of the processes waiting for a 0 value of that element. And finally the last possible value of this semop is if it is a negative number. So if it is a negative number, semop adds the semop value. So this is the function, so don't get confused, this is the function semop and this is the value, this is what we have, this value, right, which is present inside the structure. So when I talk about semop, I am talking about the function. When I talk about sem underscore op, I am talking about the value of the buffer that is that is passed as an argument to the function. So this value corresponds to the semaphore element value, provided that the result would not be negative. And if the operation would make the element value negative, then semop blocks that process on the event that the semaphore element value increases. If the resulting value is 0, then the semop awakes the processes that are waiting to become 0. Okay, so this is the representation or significance of the semop value in performing the operations on the semaphore. So this is about semaphore, and in our next session we will look into shared memory. I'll see you all in the next one. Thank you.